Welcome to this explainer. Whenever I look at a block of metal, or just a glass of water, I can't help but wonder what is genuinely happening at the absolute smallest level of reality. Today, we're going to treat the atom kind of like a bustling, microscopic, high-rise apartment building. We aren't just going to look at the outside of the building, we're going to learn the precise rules for exactly where every single electron tenant lives. Because by decoding these rules, we actually unlock the secrets to how every single element in our universe behaves.
So here's our roadmap for decoding this microscopic rule book today. First, mapping electron addresses. Then, the rules of electron housing, followed by periodic table building blocks, the atomic rule breakers, and finally, ions and free radicals. Let's jump right in.
To set our baseline, let's talk about electronic configuration. It's essentially the exact mailing address of an electron. It is a system that tells us the specific energy level, the subshell, and the precise orbital location of every single electron within an atom. Understanding this arrangement is absolutely crucial. It's basically the master key to chemistry, because it's these outermost electrons that dictate how atoms bond, react, and ultimately form the physical world around us.
Part 1. Mapping electron addresses and learning the language of the atom. Take a notation like 1s1. It looks like math, but it's really a highly organized map. That large number up front, the 1, is the principal quantum number. Think of this as the floor of our apartment building. It represents the main energy level. The letter next to it, in this case S, represents the subshell, or the specific apartment type on that floor. And finally, that little superscript number, that tells us exactly how many electron tenants are currently living in that specific apartment. So 1s1 simply means one electron is living in the S subshell, light down on the first floor.
Part 2. Rules of electron housing. This is all about electrons, spin, and personal space. Now, physical reality actually bridges perfectly with the diagrams we draw. Electrons aren't just static dots. They act like tiny spinning electrical charges rotating on their own axes, either clockwise or anti-clockwise. And when we use box notation to map out the atomic orbitals, the individual rooms in our apartment, we represent those spinning electrons using up and down arrows. An up arrow might mean clockwise, and a down arrow means anti-clockwise. But here's the crucial part. How do these electrons actually decide to fill those boxes? Well, because they are negatively charged, electrons naturally repel each other. They literally hate sharing. We call this spin-pair repulsion. So they follow a very strict three-step process. First, they will always spread out and take separate empty orbitals in a subshell if they can. They want their own room. Second, they'll only pair up when there are absolutely zero empty orbitals left. And third, when they're finally forced to share a room, they will adopt opposite spins. One up arrow, one down arrow. This opposite spinning creates tiny magnetic fields that actually help minimize the repulsive force between them.
Part 3. Periodic table building blocks. How electrons literally shape the table.
The periodic table isn't just some random grid. It's a direct reflection of this exact electronic configuration. The table is neatly split into distinct blocks: the S block, the P block, the D block, and the F block. And an element gets placed into one of these blocks entirely based on which specific subshell its outermost or valence electrons are currently filling. For example, all those highly reactive metals in groups 1 and 2, they're in the S block simply because their last added electron went straight into an S orbital. It's a beautifully structured system. Of course, as atoms get larger, writing out every single tenant's address gets exhausting pretty fast. A full configuration lists every single electron starting way down at the ground floor, 1s. For heavy elements, your hand would literally cramp up. To save time, chemists use a brilliant shorthand method. They swap out the entire inner core of electrons with the symbol of the nearest previous noble gas in square brackets, like argon, Ar, which cleanly accounts for the first 18 electrons. Then they just write the addresses for the few remaining outermost electrons. It's an elegant way to focus on the valence electrons that actually do all the chemical heavy lifting.
Part 4. The atomic rule breakers. Because sometimes exceptions create stability.
Up until now, we've relied on the outbow principle, which essentially says, always fill the lowest energy levels first before moving to higher ones. It's a very logical, step-by-step process. But in chemistry, nature ultimately prefers stability above all else. So what happens when breaking that normal filling order actually results in an atom that's energetically far more stable?
Well, that brings us to chromium and copper. These are two
fascinating exceptions to the rulebook. If we followed the standard rules, we'd expect chromium to end in 3d4 4s2. But its actual real-world stable configuration is 3d5 4s1. An electron is literally promoted from the 4s apartment up to the 3d apartment. Why on earth would it do that? Because the 3d subshell holds a maximum of 10 electrons. By moving just that one electron, chromium gets a perfectly half-full d subshell with 5 electrons, which is uniquely stable. Copper pulls the exact same trick to achieve a completely full 3d10 subshell. Nature will happily bend the rules of the low-energy fill just to get that incredible stability of symmetrical, half-full, or fully full subshells.
And finally, Part 5. Ions and free radicals. Losing, gaining, and splitting electrons.
When metals react, they tend to lose electrons to form positive ions, called cations. You'd probably think they'd lose the very last electron they gained, right? Well, for transition metals, in the d block, we get a major plot twist. When atoms of a d block element ionize, they actually lose their electrons from the 4s orbital before they lose them from the 3d orbital. So when titanium forms a 2+ ion, it ejects its 2 4s electrons first, leaving those 3d electrons perfectly intact. It's a really critical quirk of transition metal chemistry.
But ions aren't the only way electrons get separated. Sometimes molecules get hit with energy, like UV light, that causes their covalent bonds to break entirely. If a bond splits perfectly evenly, a process we call homolytic fission, each atom takes exactly 1 electron from the shared pair. The result? A free radical. This is a chemical species with a lonely, unpaired electron, which we write using a distinct dot next to the chemical symbol. And because they have an unpaired electron desperately seeking a partner, free radicals are highly, highly reactive. When we look at the box notation for a chlorine-free radical, that abstract idea becomes incredibly concrete. If you look at the outermost 3p subshell, you'll see 2 boxes containing paired electrons, one spinning up, one spinning down. But in that very last box, there is a single, solitary up arrow. That is our unpaired electron. That single physical dot is the exact reason why a chlorine radical is so aggressively reactive in our atmosphere. So considering everything we've just mapped out today, from strict department rules to stable rule breakers, I'll leave you to ponder this. Isn't it absolutely wild that a single, microscopic, unpaired spinning electron can completely rewrite the chemical behavior of the matter that makes up our entire universe? Keep asking questions and keep looking closely at the incredibly precise rules that build our physical world.